C1. Bringing the negative over, so I have the natural log of TE minus T is equal to negative RT plus the negative of the previous constant. So E to the negative RT plus C2 is equal to TE minus T. Again, TE is the temperature of the environment or the surrounding area. And so the temperature at some point in time is going to be, bring that over and flip it. So this is the temperature of the environment minus E to the negative RT plus C2. This is rather awkward. I know that this whole thing right here is E to the negative RT times E to the C2. So I just have yet another constant. So I have T is equal to the environment temperature minus some other constant times E to the negative RT. So let's do a little plug and chug here. I know that when time is equal to 0, the temperature of time 0 is equal to whatever the initial temperature of the probe is. So if I plug in 0, this becomes 1, and so I get initial temperature is equal to the environmental temperature minus C3. So C3 is just TE minus TI. Just the difference in the initial temperature of the probe and the environment. All right, surely I've got dark markers around here somewhere. Wow, good deal, right? Oh, there's one. So I now have the temperature as a function of time is equal to the environmental temperature minus the environmental temperature minus TI. E to the negative RT. Let's see if this works. As T goes to infinity, this term drops out because this becomes E to the negative infinity, which is close enough to 0. And so we end up with a temperature equal to that of the environment. So, what are the chances this is actually going to come out to be some sort of exponential? Well, it's curved nicely. Curve fit, blue temperature. I know it. Oh, I'm including red marks. Analyzing curve fit. And it seems to go awry at some point. I'm assuming that you can see the absolute beauty of, if you can't see it, it's a perfect fit. If you can see it, the black line and the blue line are a little bit off. It's as if this is not an ideal situation. Oh, the natural logarithm fit incredibly well, or comparatively speaking. Now, the first example we did, when I brought the stuff over here and it's now erased, we had the final temperature was somewhere in between the two temperatures. But now I'm making the assumption that the final temperature is going to be equal to that of the environment. What's the difference? How can I justify saying the final temperature here is that of the environment, whereas the first time it was not?
there was insulation on the first experiment?
That's part of it.
Well, there's just a whole lot of the air, and the impact that will have on the air is relatively little.
And that's the big difference right there. In the first case, my environment was very small. In the second case, the environment was huge. So we assume that the temperature of the air around here is not appreciably changing. Because whatever energy is being lost, spread it out over all the air in the room, or all the volume in the room, it comes out to something inconsequential enough. And at least I'm assuming that it did not change much. I'm not feeling like I'm sweating excessively because of the loss of temperature there. Potentially you are. You might be more sensitive to it than I am. All right, questions to hear? All right, so next up. So we've talked about I put energy into a system and the temperature changes. Obviously, there are some limits on that. If I take ice at negative 10 degrees Celsius and I put energy into the system, yeah, I'm going to get a temperature change until it starts to melt. So what happens at the melting point? Well, first off, if it's dealing with a change in temperature, we have Q is equal to mc delta T. And I also want to point out some vocabulary here. This is known as the specific heat, and you can also call it specific heat capacity. In thermodynamics, if you see the word specific, that means that you're going to have to multiply by something. This is a much more general term. So you've got mass times the specific heat, because this is the amount of energy to raise the temperature a degree Celsius or 1 Kelvin per unit mass. Sometimes referred to the specific heat specific mass heat capacity or mass specific heat capacity. Generally, if you say specific heat, it's the mass one. If you just talk about heat capacity, the mass is already taken into account. So if I have an object with a specific heat of let's make it a different number, 2 calories per gram degree Celsius, this is a specific heat because there's a mass unit right here. I'm gonna have to multiply by a mass in order to get the actual value for that particular object of how much energy it takes to change it 1 degree Celsius. If my mass is 4 kilograms, my specific heat would be 8 calories per degree Celsius. This is specific to whatever I'm dealing with in that situation. It seems to be a general rule that if the word specific shows up, that means you're going to end up multiplying by the mass or the number of moles or whatever it happens to be. And also differentiated by the lowercase and uppercase.
For that one, is that there's no, or it's the mass being in kilograms and the specific heat being calories per gram, there's no difference there.
The formula would change to that.
Well, specifically for the specific heat, it's 2 calories per gram.
Yeah, because
But then-
specific is going to have that extra unit at the bottom.
So multiplying it by a kilogram doesn't really have any.
Oh.
Okay.
Very good. Thank you. By the way, what is the specific heat of water when you're dealing with calories per gram degrees Celsius?
1.
Yeah. Oftentimes, water is whatever unit you're working in is equal to 1. In whatever, it'll be 1 in whatever units were fashionable at the time.
So is that what calorie is defined as?
Yeah. Based upon
And is
the,
that kilocalorie or uppercase, lowercase? c?
all right, that is, that CAL is the physics engineering calorie.
And that's what you have there.
That's what I have there. If you see a kilocalorie, that's sometimes called a calorie with a big C, which is the dietary calorie. So if you consume 2,000 dietary calories, it was actually 2 million science calories. And while we're on the subject of calories, the conversion from calories to joules. I see different numbers, which seems bizarre to me because there should be, if there really is, they're both measuring energy, so they should both, there should be some set translation between them. And I did find a fun source that said, well, it depends on what kind of calorie you're talking about, and broke it down into conventional calories, dietary calories, thermodynamic calories, and international table calories. So if you pursue this, presumably you'll get into the nitty-gritty on that one. My dealing with thermodynamics, just never really distinguished other than food calories or dietary calories and regular ones. All right, so back to the question of what happens in the transition. So as you put heat into it, the particles are going to start moving around a little bit more excited. If it's frozen object, it's not going to move around too much, but there's still some little extra movement there within the confines of what it means to be frozen. So we get this increase in the thermal energy, which is translated to increase in kinetic energy, as mentioned earlier. When you get to the transition phase, when I'm going from ice to liquid water, what I'm doing is I'm separating the particles now. So that energy is now going into potential, a difference in the change of the potential energy as opposed to the kinetic energy, because when you do that transition, you're not really changing the temperature of that which you are separating. So if I put energy into ice, so let's start out with the temperature of H2O in all three forms. We'll put 0 there. This would be the energy you're putting into it. So it's starting out down here, you put energy into it, should be a linear relationship, until you get to the melting point. At the melting point, temperature is not changing in our nice ideal situation, but Q is, because we're putting energy in, which is just changing potential energy. Then once it's melted, it will start to increase again, up until we get to the boiling point, at which point we have another bit of separation, and then we go up to whatever temperature we're going to do, so let's say 120 degrees Celsius. The transition energies are known as latent heats. So at transition, Q is equal to the mass times the latent heat. And there are obviously two different latent heats because we got one here and we got one there. At this point right here, we have the latent heat of fusion. At the other one, the latent heat of vaporization. So for water, So the latent heat of fusion of water, 3.33 times 10 to the fifth joules per kilogram. Notice that there's no temperature aspect in there because we're not having to change the temperature here. And latent heat of vaporization for water, 2.256 times 10 to the 6th joules per kilogram. While we're here, specific heat of ice. This. Probably should organize this a little bit better. All right, so latent heat of vaporization, this is for H2O. Two point 256 times 10 to the 6th joules per kilogram. Latent heat of fusion, 3.33 times 10 to the 5th joules per kilogram. Specific heat of ice, 2090 joules per kilogram Kelvin, or degrees Celsius. And specific heat of water, 4,000 of liquid, I should say. That's L. 4186 joules per kilogram Kelvin, and specific heat of steam, 1996 joules per kilogram Kelvin. All right. So if I have a half kilogram of water, how much energy does it take to take it, let's say half kilogram of ice, how much energy does it take to get that water from negative 10 degrees Celsius up to 120 degrees Celsius? Well, you do it part by part. First, we need to get the ice up to the melting point. So going from negative 10 degrees Celsius to 0 degrees Celsius, Q is equal to MC ice delta T. I said a half kilogram. Everyone recently sat markers. So 0.5 times specific heat of ice, 2090 times temperature of 10. All right. Now I melted. I go from 0 degrees Celsius to 0 degrees Celsius. This is just melting. So Q is equal to MLF. .5 times 3.33 times 10 to the 5th joules per kilogram. Couldn't have made it a third of a kilogram. So 66,000. So 300,000 divided by in half, that can't be right.
Think so.
Two, not five. Once, and then I got six.
Yeah.
Is it, okay. So it takes considerably more energy to melt it than it does to actually get it up to melting temperature. Now we have to heat it up to its boiling point. We're back at MC delta T, H2O liquid, times time. So we got our 0.5 times specific heat in joules, 4186 joules per kilogram Kelvin, times 100 Kelvin, I guess. And now we have to actually boil it. So we're going from 100 degrees Celsius to 100 degrees Celsius. Because we're not having a change in temperature here, we're using the latent heat formula, so ML, this time vaporization. So 0.5 times 2.256 times 10 to the 6th. One, 2, 8, 0. Oh, so one too many, that's one too many zeros.